Hello everyone. So in the last lecture we have gone through the construction of NPN transistor. So let's start with the next topic, that is the working of NPN transistor. Okay. So in the last lecture we have seen this diagram, right? So first one is the emitter, then second one is the base, and third one is the collector region. Right. So the N is made up of a is of emitter region, and P is of base, and again N is of collector, right? So that is why you can see the N and P, between the N and P we have given EB, right? VEB. So EB is nothing but emitter and base junction, right? Because this is emitter and this is base region. So this is emitter and this is base, right? So it is a emitter base junction, and this is base, right? And the last one is collector, so it is a collector base junction. Okay, so this is a emitter base junction and this is a collector base junction, right? So the voltage applied here is a VEB. V is for voltage, right? And EB is for emitter base junction. Similarly here V is for voltage and CB is for collector base junction, right? So the current flowing here is IE, right, in this direction, and here it is IC in this direction. So we will understood why it is in this direction, that direction, right? All we will see in this working of NPN transistor. Okay, now first of all let us see what is the biasing of this voltage. Okay, so you can see uh, positive terminal of this battery is connected to P region, right, and negative terminal is connected to N region, right? So don't you think that VEB will be in forward bias, right? Because P type semiconductor is connected to positive, N type semiconductor is connected to negative, so this one will be in a forward bias, right? So, and we all know that what will be in the what will happen in the forward bias. These free electrons, right, will try to enter in this region, depletion region. Why? Because this is a negative charge and electrons have also negative charge, so negative will repel each other, and that is why this electron will get pushed towards this side, right, and hence it will enter into the P region. Okay, but what happened in the P region? In P region we have a few number of holes. Why? Because in the construction we have understood that P region is lightly doped, right? So if P region is lightly doped, we have a very small number of holes available in the P region. So the electrons which is getting moved towards the P type region, it will, in that P type region, in that P type semiconductor, the electrons will get combined with the holes, but since there are very few holes are available, there will be very few number of combination, right? And that is why it will constitute the current which is a base current, but base current will be very small. Why it is very small? Because there is a very few number of combination, right? And why there is a few number of combination? Because there are very few number of holes left for the combination. So what will happen now? Okay, now we will get small current here, but the rest of the electron will again enter into the N region. Why? Because you can see here, this is in forward bias, right? How? Because this is a N type. N type is connected to positive, and this P type is connected to negative. So what will happen? The electron will get towards this side because it will get attracted by this positive terminal. Okay, so the electron will come to this side, and so let's see what happened once again. First, here we have free electrons. This electron will enter into the base region, few electrons will combine here, and the rest of the electron will go in this region. And in this region, that is in collector region, we already have free electrons, right? And now the emitter electrons from the emitter region will also coming towards here, right? So what will happen? These electrons will again travel to this area, right? So you can see the direction here. We are seeing one thing, and the rest of the electrons we can see here. So this is how it works, right? So we all know that the direction of the current is always opposed to the flow of electron. Always it is in the opposite direction. to the flow of the electrons, right? Electrons are moving in this direction, right? So we have a current in this direction, that is why it is a ammeter current. And here again, because current is moving in this direction, so sorry, electron are moving in this direction, so the current will move in this direction, right? So we can say that IE, this current is nothing but this current plus this current, right? That is IB plus IC is equal to IE. So let us we go through the statement. Working of NPN transistor, the forward bias at EB junction will cause the electron to flow from N type to P type semiconductor, right? We can see here, this is the EB junction, right? And it is in a forward bias. So what will happen? The electrons will get repelled from this force and will try to move into the P type region. Correct? Since the base is lightly doped, few holes are available to combine with the electrons from the N-type semiconductor. So we all know that base is lightly doped. That is why very few holes are available, and that hole will combine with the electrons from the N-type semiconductor. Why? Because N-type semiconductor is now trying to enter into the P-type region, right? Hence, a small current IB will flow across the B junction known as base current, right? So you can see here IB, it is nothing but a base current. The remaining electron will again cross the junction and enter into the collector region, right? So the electron which was coming from this N-type region, where it will go, right? So of course it will go again to the collector region. So the remaining electrons will again cross the junction and enter into the collector region to form the collector current, that is IC. Okay. So you can see I is nothing but I is the denotation of current and C is nothing but collector. So here you can see that IB, IC and all these things, right? So finally the emitter current IE is the sum of the base current and collector current. Okay. So this is the working of NPN transistor, and we have to go. So what is the last line? IE is equal to IB plus IC. So this is a very important equation because it will help us to derive the relation between alpha and beta. We will see all these things in the further lecture. Okay. So this is the working of NPN transistor. I hope you understood. Let us go to the next topic. Configuration of BJT. Okay, so let us understood what does it mean. Okay, so configuration means how you will configure, means in what are the different ways to connect bipolar junction transistor with DC supply. Okay, right, so that is we have to play with the three terminals of that BJT. Okay, so in any circuit only two terminals are required for input and output, right? But the transistor consists of total three terminals, right? So what will happen? One terminal is always made common to both input and output, and depending on that we have a three basic type of configuration of BJT. Okay, so the first one is common base configuration. So as the name suggests, base will be connected to both emitter and collector. Okay, then in the second one we have a common emitter configuration, right? So that what does that mean here? Here what we will do, emitter is connected to both collector and base. Okay, then in third one we have a common collector configuration. So right, so collector will be the common between the rest of the two, that is emitter and base, right? So in short we can say that it is a CB junction, it is a, and next one is a CE junction, and last one is a CC junction. So in all these junctions what we have to see, we have to see the circuit diagram. Then depend on the circuit diagram we will understood the input characteristic and output characteristic. Okay, so in all the three configuration we have to see these three things, these three things, that is common base, so that is a circuit diagram, then input characteristic, and the next one is output characteristic. Okay, So we will see all these things in the next lecture. So we will stop here. Okay, thank you.